Planet Earth has a lot going on inside it, from human-made to natural. However, when you step outside the planet, there is far more going on out there, including, as astronomers just discovered, visitors from interstellar space that are heading toward our planet. What are these objects hurtling toward the Earth, and will they collide with the Earth? Stay tuned as we bring you details of the latest interstellar visitors to show up and are heading toward the Earth. Ka Epaoka Awela is one of the latest visitors to enter our solar system. Ka Epaoka Awela is a tiny asteroid that orbits the Sun in the opposite direction as the majority of the solar system's other components. It was identified by astronomers from the Pan-STARRS survey at Haleakala Observatory on the Hawaiian island of Maui. It was given the Hawaiian name the Jupiter Trickster by a Hawaiian language program dedicated to naming objects discovered with Pan-STARRS. The Panoramic Survey Telescope and Rapid Response System Pan-STARRS is a program that uses telescopes and cameras to survey the sky for moving or variable objects, such as asteroids, comets, supernovae, and other celestial phenomena. It's a collaboration between the University of Hawaii Institute for Astronomy, MIT Lincoln Laboratory, Maui High Performance Computing Center, and Science Applications International Corporation. The program is funded by the U.S. Air Force and NASA. Ka Epaoka Awela is an interstellar visitor who was captured by the gravity of the Sun 4.5 billion years ago. This is the notion advanced by astronomers Fatih Namuni and Helena Morais, who utilize computer simulations to trace back the asteroid's orbital history and discovered that it started in interstellar space. According to their research, this asteroid was one among numerous asteroids that roamed between the stars in the galaxy's early days. The Sun was part of a stellar nursery at the time, a cluster of stars that formed from the same cloud of gas and dust. Because the stars were so close together, they felt each other's gravity far more intensely than they do now, allowing asteroids to be pushed from one star system to another. Ka Epaoka Awela was one of these roving asteroids that happened to collide with the nascent solar system and become entangled in its gravitational field. Unlike most other asteroids caught into prograde orbits the same way as the planets, Ka Epaoka Awela has a high inclination and a retrograde orbit, making it less vulnerable to planetary impacts. But how do scientists determine that an object is from interstellar space? One of the primary methods is to study its orbit. Every object in the solar system orbits the Sun in an elliptical orbit that is modified by the gravity of other bodies. Several factors, including the semi-major axis, eccentricity, inclination, ascending node longitude, and argument of perihelion, determine the form and direction of these orbits. Astronomers can determine an object's orbital energy and angular momentum by measuring these parameters, which are conserved quantities that depend only on the mass of the Sun and the object itself. A positive orbital energy indicates that an item is not tied to the Sun and will eventually depart the solar system. And if an object has a high angular momentum, it has a high inclination or eccentricity, indicating that it did not form in the solar system. These characteristics can assist astronomers in identifying interstellar objects among the solar system's millions of known asteroids and comets. The Pan-STARRS survey in Hawaii, for example, detected the first confirmed interstellar object, Oumuamua, in 2017. It had an extremely eccentric orbit with an eccentricity of 1.2, indicating that it was not elliptical but rather hyperbolic. It also had a high inclination of 122 degrees, indicating that it was practically perpendicular to the solar system's plane. Another approach to tell if an object is from another solar system is to examine its makeup. Depending on their origin and history, interstellar objects may have different chemical and physical properties from those found in the solar system. Interstellar objects, for example, may have distinct isotope ratios of particular elements, such as carbon or oxygen, which reflect nucleosynthesis processes in their parent stars. And astronomers can use spectroscopy to explore the composition of interstellar objects, which is a technique that analyzes the light emitted or reflected by an object at different wavelengths. The spectral signatures of various molecules and atoms reflect their presence and abundance. Oumuamua, for example, showed no evidence of water or other volatiles in its spectra, unlike the majority of comets in the solar system. Astronomers can detect whether an object is from outside the solar system with high confidence by combining orbital and compositional analyses. However, because interstellar objects are generally weak, rapid, and elusive, these procedures are not always simple or decisive. As a result, additional observations and data are required to determine their nature and origin. Now, Ka Epa Oka Wella found a safe haven in Jupiter's co-orbital area where it could escape close encounters with the planet and keep its orbit stable for billions of years. This region is occupied by Trojans, which orbit ahead of or behind Jupiter at two stable positions known as Lagrange points. Ka Epa Oka Wella differs from the Trojans in that it orbits Jupiter on the other side of the planet and crosses its path twice every orbit. Based on its absolute magnitude of 16 and an approximated albedo of 0.11, Ka Epa Oka Wella has an estimated diameter of roughly 3 kilometers or 2 miles. This equates to the size of a small mountain or a major city. Ceres, the largest asteroid in the solar system, has a diameter of approximately 940 kilometers or 580 miles. Compared to 2015 TC25, the smallest known asteroid, which has a diameter of only 2 meters or 6 feet. However, determining the size of asteroids is difficult since they are frequently irregularly shaped, have fluctuating reflectivity, and appear very small in the sky. As a result, the diameter of Ka Epa Oka Wella is simply an estimate that may change as more observations and data are collected. Radar imaging, which can disclose its shape and surface details, can be used to gain a more exact measurement of its size. However, unfortunately, Ka Epa Oka Wella is not a good radar imaging target since it's too far away from Earth and too weak to be seen by present radar capabilities. Ka Epa Oka Wella made its closest approach to Earth on May 17, 2018, coming within 2.3 astronomical units, or about 344 million kilometers, or 214 million miles of our planet. Even at this distance, only huge telescopes could see it. However, another method is to use optical or infrared measurements from space telescopes like Hubble or Spitzer. These telescopes can determine its size and composition by measuring its brightness and color at different wavelengths. However, because it's not a high-priority target for scientific inquiry, Ka Epa Oka Wella has yet to be detected by any space observatory. And unlike most other bodies in the solar system, Ka Epa Oka Wella orbits in the opposite direction of the Sun's spin, or retrograde. It also has the same orbital period and distance from the Sun as Jupiter, making it the giant planet's co-orbital companion. Another example of an asteroid with retrograde orbit is 2013 LA2, orbiting the Sun at a very high inclination of 175 degrees. It is one of the few known members of the Phoebe group, a population of retrograde TNOs that may have originated from Saturn's moon Phoebe. Now, several characteristics describe Ka Epa Oka Wella's orbit. Its semi-major axis, which is half of its elliptical orbit's longest diameter, is 5.13 astronomical units, or AUs, or around 767 million kilometers. This corresponds to Jupiter's semi-major axis of 5.2 AU. Its eccentricity, which indicates how far its orbit deviates from a perfect circle, is 0.38, indicating that it has a very long orbit. Its perihelion, or closest point to the Sun, is 3.19 AU, while its aphelion, or farthest point from the Sun, is 7.09 AU. The orbital period of Ka Epa Oka Wella, or the time it takes to complete one revolution around the Sun, is 11.65 years, or 4,256 days. This coincides with Jupiter's orbital period of 11.86 years, or 4,332 days. This means that Ka Epa Oka Wella and Jupiter are in a 1-to-1 resonance, which means they complete one orbit for each other. Because Ka Epa Oka Wella orbits Jupiter in the opposite direction, it crosses its path twice every orbit, leading to close encounters every 6 years. Ka Epa Oka Wella's inclination is 163 degrees, which measures how much its orbit tilts with regard to the plane of the solar system, the ecliptic. This means that its orbit is nearly perpendicular to the ecliptic and that it moves backward. It has a longitude of 307 degrees for its ascending node, which marks where its orbit crosses the ecliptic from south to north. It has a perihelion argument of 257 degrees, which indicates where its orbit reaches its closest point to the Sun relative to its ascending node. The orbit of Ka-epa-Oka-Arwella is incredibly steady and has been for billions of years. It avoids close collisions with Jupiter by staying on the planet's opposite side and being shielded by two stable locations known as Lagrange points. These are areas where the Sun's and Jupiter's gravitational forces balance each other out, allowing small bodies to maintain a stable position relative to both bodies. Ka-epa-Oka-Arwella orbits around one of these points, L3, which is found 60 degrees off Jupiter's orbital plane. However, the asteroid Ka-epa-Oka-Arwella is not the only one with an interplanetary origin. Namuni and Marais discovered 18 more asteroids with high-inclination orbits that could be captured from beyond the solar system. These asteroids are centaurs, which are ice bodies with erratic and unstable orbits that orbit between Jupiter and Neptune. The team looked at centaurs and trans-Neptunian objects with high orbital inclination relative to the planet's orbital planes, which sometimes brought them near to polar orbits. And some of these objects, like Ka-epa-Oka-Arwella, have retrograde orbits. With moderate to high eccentricities, centaurs' orbits may be inclined by a few degrees with respect to the solar system's invariable plane to almost 180 degrees, resulting in retrograde motion. Their orbital features are frequently interpreted as evidence of their violent past in the solar system, a notion reinforced by their so-called instability. If a centaur orbit is integrated forward or backward in time, it will always either collide with the Sun and the planets or be ejected from the solar system. The survey includes 17 centaurs with orbital inclinations more than 60 degrees, as well as two trans-Neptunian objects that orbit past Neptune. The researchers used the known orbits of these objects to generate many clones of each one in order to mimic their orbits back in time 4.5 billion years. The origin of Ka-epa-Oka-Arwella and other asteroids in interstellar space has significant implications for our knowledge of the formation and evolution of the solar system and other planetary systems. It shows that in the early phases of the galaxy there was a considerable flow of material between different star systems, and that some of the asteroids we see now may have formed around other stars. It also suggests that some of these asteroids may contain biological chemicals or perhaps life forms from other planets.